Well, good morning there, physics students. It is May 7th, 2020. Time to do some collisions. So today, I can explain the difference between elastic and inelastic collisions. I can perform conservation of momentum calculations. Yes, more of those. All right, so sometimes in collisions, objects bounce off each other. Sometimes in collisions, objects stick together. If they bounce off each other, the word we use for that is elastic. When they stick together, the word that we use is inelastic. Okay? So, elastic objects bounce back. Now, there's a part over here. When we call a perfectly elastic collision, there is no loss of kinetic energy. So if you were looking at an example of a perfectly elastic collision, not only can you apply conservation of momentum, but you can also apply conservation of energy to that situation. Now you might already, I hope, have the idea that, gee, that sounds really unlikely for there to be no loss of kinetic energy. And you're right. But we have situations that the loss of kinetic energy is really, really minimal. So we have situations that approximate total or perfectly elastic. Inelastic collisions, again, the objects stick together. So if they just totally stuck and there was no conservation of energy involved, I guess, I don't know if you ever hear the word perfectly inelastic collision, but you could look at this overall as being a continuum. So let's say I got a continuum, and over on this side I have elastic, and over on this side I have inelastic. My spelling brain just stopped on me, I'm sorry. And we have everything in the middle, right? I mean, a lot of times, aren't you going to have situations where things, you know, they might kind of bounce back, but not perfectly? And so, you know, we have collisions that are going to be mostly inelastic with a little bit of bounce back, and they're going to have mostly elastic, but a little loss of the kinetic energy. So over here, this extreme would be the perfectly elastic collision. There's a whole range of things. Now, the concept of conservation of momentum applies to all of these. Conservation of kinetic energy only applies here. So you do have to be careful. Conservation of energy gives you a second way to double check some types of problems. It gives you a way of trying to get extra information out of some types of problems, but you can only apply conservation of energy to the perfectly elastic collisions. All right, so let's just try some examples. Here we got some bumper cars, okay? Mr. Rupp is sitting in this bumper car, so it's really, really massive, 345 kilograms. And, you know, last time I tried this, I have tried this at Valley Fair, I stepped that pedal all the way down to the floor, and that car just doesn't want to move very much. So I've got just a little bit of velocity, 3.5 meters per second. Okay? So here comes one of my students, 258 kilograms, student plus car, and they're moving a little faster, 5.5 meters per second. We're going to hit. I don't know if this is an elastic collision, an inelastic collision, whatever it is. Doesn't matter. What I'm going to tell you is that the mass of the two cars doesn't change. And I'm going to tell you, after the collision, the new velocity of the student. And the student was going that way, but now they're going this way. And in case it wasn't clear, I was going that way. Now, to solve this, we really need to decide where our positive direction is. So what we have done throughout the year where we've needed it is we've said positive is to the right. Okay, so negative is going to be to the left. So this is going to be a positive velocity. This is going to be a negative velocity. This is going to be a positive velocity. Okay? We want to get, because it's going to affect our math. All right, the way I do really any collision problem is I start out with the momentum before has to equal the momentum after. Okay, so let's look at before the collision. What's moving? Well, that car is moving. It's got a mass and a velocity. And that car is moving. It's got a mass and a velocity. So I have to get the total momentum before, I have to add up the momentum of both of them. And if we think about after the collision, well, we know that car is moving. And we don't know what the velocity, it could have stopped, but we really don't know. So we're going to assume it's moving, and we're going to put the numbers in, and we're going to find out. Because what I'm looking for is, what is my new velocity here? So before the collision, let's see. I'm calling this MR. This is Mr. Rupp. So R stands for Rupp. This was MM. Do I have an M for students in my current class? Mary. Okay. So here's Rupp's car. Here's Mary's car. Okay. So before the collision, I'm going to take the mass of Rupp's car, not just Rupp, and times the velocity of Rupp. That's my momentum. And I'm going to take the mass of Mary's car plus times the velocity of Mary's car. Okay, now after the collision, well, it's going to be the same thing again, right? I'm going to have the mass of Rupp's car and the velocity of Rupp's car plus the mass of Mary's car times the velocity of Mary's car. And I hope you look at this and say, there's a problem, because these velocities are different. So don't we have to? So one of the things we do in physics a lot of times, if we got a new velocity, we just put a prime on that variable. So this is my original velocity. Here's my new velocity. Here's my Mary's original velocity. Here's her new velocity. So with that said, I should be able to plug in some numbers. So mass are up 345 kilograms times 3.5 meters per second plus 258 kilograms times negative 5.5 meters per second equals, I'm going to have trouble fitting this on the board. I think what I'm going to do, highlight that, group it together, shrink it a bit. Good luck doing that on your paper. Okay, so over here, we got mass are up, 345 kilograms times VR prime, I don't know it, plus mass of Mary, 258 kilograms times her new velocity is 0.5 meters per second. All right. Now, algebra. There's the variable that we're looking for. So I have to get it by itself. Now, that variable is multiplied by this stuff, and it's added to this stuff. So if you think about your order of operations, when I'm moving things around, it's kind of the reverse of that standard order of operations. So I got to subtract this first, and then I'll divide by that. Now, I usually like to work out all my algebra first before I plug in numbers, and for whatever reason, momentum problems, they're just always awkward. They just look ugly. They're not difficult. They just look ugly. And you got to be patient with them, work through them. I put my numbers in already. I'm going to keep going. But I can simplify a little bit along the way. For this sample problem, I had 3 sig figs, 2 sig figs, 3, 2, 3, don't know, 3, and I only gave 1 on here. It's a practice problem. I'm just going to work out this answer in the end to 2 sig figs, and we'll just leave it at that. I really want to get into the momentum and not get hung up too much on the sig figs. So I've got 345 times 3.5. I'll keep extra digits here. That's 1207.5 kilogram meters per second. Okay, plus 258 times negative 5.5 equals. So it's actually minus 1419 kilogram meters per second. I'm going to go ahead and I'm going to take this guy, I'm going to multiply it together and subtract that. So 258 times 0.5 equals, so that's negative 129 kilogram meters per second equals 345 kilograms times VR prime. Now, these things all have the same labels, so I can just add them together, you know, this plus a minus, so 1207.5 minus 1419 minus 129 equals negative 340.5 kilograms times meters per second equals 345 kilograms times VR prime. Now to get VR prime, I'm just going to divide both sides by 345 kilograms. Kilograms are going to cross off, and I'm going to be left with meters per second. Okay, so VR prime equals negative 340.5 divided by 345 negative, it says 0.9869, so 0.99 meters per second. Negative means that way. All right, just means to the left. I want to just go up here and try to reason this out. Oops, wrong way. Let's see. So I was going 3.5. Let's see. She almost came to a stop. Looks like I bounced off backwards. I don't know if I gave the most reasonable answer or numbers in this, but the math would work out. So in a real situation, I'm not sure if this is a reasonable velocity at the end for Mary's vehicle. It's very possible this velocity should have been bigger the other way, and therefore that would change my answer. So I did some guessing on my numbers. It's all right. Okay, let's look at another sample. Here we got a football player holding a ball to have mass 100 kilograms, and they're not moving, which is weird, but we're going to go with it. Okay, here comes a guy, 150 kilograms, big lineman, coming along. He's lumbering pretty good, 7 meters per second. He's going to do a form tackle. Okay? So that's an inelastic collision. Right? Boom, wrap up. Now they're both going together. So I want to know what's the velocity after the collision. What do? Momentum before equals momentum after. Well, before, this guy's not moving. So that's 0. This guy's moving. So we got mass of, I'm going to call this 1 and I'm going to call this 2. Okay? M1V1. That's all the momentum before. And after the collision, they're stuck together. So the mass is really 1 plus 2 times some new velocity. I'll call it V prime. I guess up there I called it VF. Let's call it VF. Okay? All right. So, 150 kilograms times 7 meters per second equals, what's the mass of both together? Hopefully you can do a little bit of mental math. 150 plus 100 is 250. 250 kilograms times VF. Well, I just multiply those and divide by 250. And I get VF. Kilograms are going to cross off. So 150 times 7 divided by 250 equals 4.2. Yes, I know, it should be, according to what was written, only 4 meters per second. Well, that one ended up being a lot simpler because there weren't as many objects moving. So we didn't have to have as many momentum terms. You have to account for everything that's moving because everything that's moving has momentum. Imagine we did a problem on paper where we were doing a break in a game of pool. After the collision, you'd have 16 balls moving, and they're not only moving in one dimension, they're moving in 2 dimensions. That's a little bit of a complicated problem. All right, review. Perfectly elastic collision. No loss of kinetic energy during the collision. This is an example. I was trying to draw like a Newton's cradle, and I'm going to share a video of Newton's cradle with you. Perfectly inelastic collision, they stick together and there's no rebound whatsoever. Okay? In that case, kinetic energy is not conserved. Okay, let's try another. We've got, I'm going to try to shrink this whole thing. Hopefully you can still see some of that, but we just got 2 balls, okay? This ball is 0.5 kilograms, this ball is 0.8 kilograms. This ball is moving 3 meters per second, this ball is moving 1 meter per second in the same direction. Okay, so they're both moving in a positive direction. This one's moving faster though, so it can catch up. We can still have a collision, even though they're moving in the same direction. Now this is saying that after the collision, this guy's going 2 meters per second. If that's the case, what would this one be? Again, I'm kind of making up some numbers here, so I don't know if the numbers are going to come out to a realistic problem, but it's certainly a math problem that we can try. Momentum before equals momentum after. Before the collision, they are both moving. I'm going to skip right down the algebra part this time. I'm going to go to the numbers. I'm going to take the mass, 0.5 kilograms, times 3 meters per second, plus 0.8 kilograms times 1 meter per second. Now, I like to write equations, and I would expect you to write equations. But this is the 3rd problem we've done in a row. And I know my starting equation. I know that momentum is mass times velocity. Now I'm going to go over here to after. Are they both moving? So far as we know. So let's write a term down for both. The 0.5 kilogram ball, we don't know how fast it's going. So I'm just going to put a V there. plus, we got the 0.8 kilogram ball times 2 meters per second. Okay, 0.5 times 3 is 1.5 kilogram meters per second. 0.8 times 1 is still 0.8 kilogram meters per second. 0.8 times 2 is 1.6, and we go minus 1.6 kilogram meters per second equals 0.5 kilograms times V. Add these together. 1.5 plus 0.8 is 2.3 minus 1.6. 3 minus 1 is 1.3. That'd be 0.7 kilogram meters per second equals 0.5 kilograms times V. And if I divide by 0.5 kilograms, 0.7 divided by 0.5 equals 1.4. So V is 1.4 meters per second. Within sig figs, we'd have had to say 1, I guess. When we do our problems on worksheets, we'll try to have some sig figs for you. Okay. I think I had one more sample I wanted to do today. Okay. So, shrink this again a little bit. All right, I've got some sort of projectile flying through the air at 80 meters per second, and that projectile has a mass of 1,000 kilograms. And while it's flying through the air, it breaks into two pieces. The rear piece has a mass of 250 kilograms and is now only going 20 meters per second. So the front piece has the rest of the mass, 750 kilograms. How fast would the front piece have to be going? Again, momentum has to be conserved. So the momentum before has to equal the momentum after. Well, the momentum before, this is all together, so we've got just one mass and one velocity. 1,000 kilograms times 80 meters per second. Now we look at after. This guy's still moving in the forward direction, so it's positive. We've got 250 kilograms times that 20 meters per second, plus the other piece, which is 750 kilograms times whatever that velocity is. So we've just got to solve. We've got to subtract this from both sides and then divide by 750 kilograms. I'm going to go ahead. 1,000 times 80. Duh, that's 80,000. Kilogram meters per second minus 250 times 20. Okay, I can do this. 250 times 2 is 500. 500 times 10 is 5,000. All right, so I subtract over here. I've got 75,000 kilogram meters per second equals 750 kilograms times V. So if I divide by 750, is that 100? Yeah, that's 100. I'm going to punch into my calculator so I don't make some silly mistake, but it looks like this is a problem we didn't need a calculator for. Kilograms are going to cross off when we do that. So our final velocity is 100 meters per second. It seems to me in one of the Back to the Future movies, they took advantage of this. They had a train that they were loading along. And I think they did an explosive rupture between the cars, and maybe I'm misremembering that. They had some special fuel that Doc Brown worked up also to get the train going faster, but I think they used an explosive decoupling. And so by getting rid of that mass, by trying to throw that mass back, it gives an extra push to this mass forward. So this gave a boost of speed to that front part of our rocket. I don't know if anything like that is used in multi-stage rockets in launch, how fast the decoupling takes place. I suspect maybe not really, but it might make a difference. Obviously, if one part goes back, the other part has to speed up a little bit. So, all right, there's a little variety. Again, they look ugly, but they're not really hard. You gotta make sure you're writing down your numbers, writing down your labels. I watched a video today of a guy doing some momentum problems, and I liked his approach, and he was really showing some neat things, some things that I hadn't thought about before and hadn't shared with you. But I didn't like the fact that he didn't put any labels in his calculations, and he did everything with just very basic numbers, and that's okay for demonstration purposes. I didn't like that he wasn't using labels, though. I think you mess yourself up when you don't use labels. All right, I'm going to have some practice problems for you. Good luck. Let me know if you have problems.